Okay, like yesterday we have seen now 1, 2, 3 sort of thing is there. If you are moving this towards right, having 2 power e sort of thing towards right, if you are shifting, what is that information you will be going to like lose or gain? This is shifting means 1 2 into to e power sorry 2 power e plus 1. One more bit you take, it is 0.01 into e to e plus 2. That means this information is lost. So better we try to shift that towards your what you say left side. Okay, it's up to the values what we are considering. That is a generalized what you say rule we are giving here. Okay, and next step is add the mantissa or what you say the fractions using the normal addition operation, normal full adder concepts, any sort of addition process you can take. Okay. Now, if you are getting the result to be zero, so what you have to put is the exponent has to be shifted or represented in according to the value. Okay, something like this. If the result is zero, something like if result is zero, now what you have to do? You have to represent the exponent accordingly and you can exit, because that something like if you are adding two numbers, something like positive negative, that condition or both values to be zero, you will be getting the result as zero. Only two conditions you have. Yes or no? When result can be zero? When you are adding plus 2 with minus 2 sort of thing, or something like plus n number with equivalent magnitude number. Okay. Now, if there is an overflow, there is a fraction overflow. Okay. What is that overflow? Like yesterday I have given this. Overflow is normally what is our format we are putting is 1.m format. No? Now, if this bit is not equal to 1, okay, then we can say that there is an overflow. Okay, if there is an overflow, you have to adjust the information. That means you have to do the right shift
Yes, ma'am.
operation. Yes. So do the right shift operation and you have to adjust the exponent. Okay. So if the overflow of result, then shift towards right. Then add 1 plus to the exponent. Okay. If it is fraction is not normalized, one more adjustment what we have to see is if the fraction is not normalized, then again you have to shift left. Shift left means something like this. Say if you are getting an value something like the result is something like this, if you are getting into 2 power exponent. Now this is not normalized, we say. Now we have to shift this towards left and you have to adjust the exponent. That means decrement the value. E minus, left shift and do E minus 1. Okay. Now again you check the exponent overflow, something like exponent overflow yesterday we have seen something like minus 127. That means your bias of 127 format you are taking, the most minimum value to the maximum value within this limit, if your exponent is there, then it is in a position to be expressed in your 1.m IEEE format. If not, you have to adjust this exponent by doing the fraction adjustment. Yes, the fraction has to be adjusted, that means shifted towards left or right. Okay, this also yesterday we have seen. So something like a flow chart sort of thing if you have to take. You have done the experiment in your lab, two batches, two sections. Yeah, completed everyone.
Yes, ma'am.
So flowchart is needed. A flowchart is needed, or shall I share the flowchart pick as uh, like pick to the group? You can
Share
cross
the picture,
verify.
ma'am.
Yeah, yeah, you can. You can. Yes, yes. You can compare that with your flowchart what you have implemented. Okay. So steps will be general steps of addition will be something like this. Like yesterday we have seen that multiplication and division also. Okay. Now we'll move towards the next topic, that is your Mips. Now this is something little bit an extensions of your microcontroller. I think you are remembering that topic of microcontroller. Yes, microcode was there. Still you remember it? Okay.
The
In
single
that,
address, no, ma'am.
yeah,
That one is single address and the dual address.
little bit louder, little bit.
Microcode is that only, no, like single address and double address.
Yes, yes, yes. The
Yes,
qualifier
ma'am.
element. Yeah.
Yes, ma'am. We remember.
So in that element, what we were taking is something like instructions only. Those were instructions, no? Like something like you had jump address, true address, false address, something. These elements we have seen. Now, what is the purpose of these instructions actually? This is something like when you are programming, you are writing a program, how your processors are evaluating these steps. That means the instructions what you are giving to the system. So how it can be taken as something like main program and subroutine programs we call. These are to like this comes in your microprocessors actually. These terms you'll be getting that in microprocessors. Like when you are performing some evaluation of codes or a program, you will be giving the complete design in the format of instructions, and these instructions will be provided something like uh, with what type of data you are accessing, or what type of iterations you are doing. Something like you can say you are addressing arithmetic logical instructions. What can be all these arithmetical logical instructions? All your addition, subtraction, multiplication, division comes under your arithmetic sort of thing, and logical anyhow we are used now, and or logics, or the conditional evaluations and all. So arithmetic logic operations will be performed, as well as something like subroutines thing. Again, we have seen this in your 2910 microprogram sequencer, where there was a pipeline register. You had some thing like stack, where there was a return address sort of thing stored and all. That means when you are deviating from the main program, some interruption you are doing here, you are like stopping the main program, and you will be going to the subroutine program and perform the iteration here, then come back to the main program. This is the format what we have to perform. That means there needs some sort of what you say, an element of interlinking between the instructions. What is this interlinking means is, say a step 1, step 2, and so on. These instructions you are giving in the form of steps, say. When you are performing these in a sequential order, one by one, when there is a link, or what you say, an outcome or output coming out from this step 1 after evaluation, if this output will be guiding the second step, and this output will be guiding the next step, and so on. That means there is a dependency of performing the next iteration based on the previous iteration. Then Until this first step is completed, you should not proceed to the second step. Am I like a little bit clear now? If there is a dependency of second instruction on first instruction outcome, until the first instruction outcome is generated, the step 2 should not be processed. Something like fewer times what happens is when the iterations are performed, your processors are very fast enough. They're like before getting any proper output from the previous stages, it will be proceeding to the next iteration. So that sort of things, if you want to delay in our systems, in normal digital systems, what we said for synchronization, use a d flip flop in the path and make the two two paths equal. Yes or no? This type of synchronization we have seen. Here what we do is, until this output, first output is generated, we try to give what is called as no operation instruction. Okay, so how many times or how many no operation instructions you have to give is until the previous step output is ready for the next step. Okay, these are something like the basic steps of your microprocessor. Okay, now this microprocessor is a complex digital system. This is the most complex digital system. Okay, and actually this Mips technologies, like the one who produced, the manufacturer, they have produced this as Mips 2000, R2000. Sorry, R2000 is the Mips, and this is subset of what you say Mips processor, and that subset of Mips processor, subset is something we name it as ISA. What is this ISA is? Instruction set architecture. Okay, like this Mips technologies, this Mips processors implemented based on the instruction sets, and this architecture denotes the instruction. It will be as if it is an assembly language, we can say an assembly language where it is giving the continuous set of instructions to be performed by the processor. Okay, something like here assembly language means when you are giving the instructions, that instructions can be of many format. That means addressing modes, we say. There are plenty number of addressing modes, something like a register addressing mode, direct addressing mode is there, or immediate addressing mode is there. What are these fellows? We'll try to see here. Something like register addressing means when you want to transfer a data from register to register. Okay, normal register is a flip-flop for us. Now if you take for microprocessor sort of thing, we say that it is a memory location. Okay, storage element, one set of registry data transferring into another set of registry data. Okay, that is one type of instruction. Direct instruction is something like we try to specify the memory location or the register into which we want to store the data, and that will be given in the instruction. Okay, immediate means something like say a register is mentioned, and what is the value you want to have. All these arithmetic logical operations performed with respect to a value, constant value. Okay, something like if I take add uh, AB, something, if I am saying this is the content of B is added with content of A. That means this is our registry format. This content of B will be added to content of A, and it will be stored as a result in this A accumulator. Now add immediate, if I say add immediate, I indicates immediate. All these we call them as opcodes. 100. What is the meaning of this is 100 is a constant. This value will be added to the content of A, and that will be stored back into A. Okay, that sort of instructions. All these things we call them as opcodes. These are opcodes, or what you say, instruction codes, we say. Okay. So like all this MIPS instruction was first developed, and that was mentioned as a RISC or CISC processors. What is this RISC or CISC is? Um, RISC is a full form, we can name it as reduced instruction set computing. Reduced instruction set computing. CISC is SISC is like we can say that it is complex instruction set computing. Like these two are like antonyms, we can say. That means the instruction size is huge here, but this is a little bit what you say, compact. RISC instructions are compact when compared to the CISC instructions. Okay, somewhere in 70s and 80s, this Intel and Motorola people, they started developing this type of addressing modes, and that was again converted into like a complex set of instructions. And what is the deviation that was there is how many number of addressing modes they have. This will be having multiple addressing modes, whereas this has only two addressing modes. Say that means simple. It is very simple in giving the instructions compared to the CISC processors. Okay, always a better option in comparison to, like if you want to reduce the number of instruction sets in your programming, instead of going for CISC aspect or CISC architecture, RISC philosophy is considered better. Okay, like this MIPS, it is a normal MIPS technology is the fellow which produced this RISC processor. Actually, this what you can say is this technology, they have taken that as the MIPS is an element of this risk philosophy, where this MIPS is a microprocessor without a hardware interlock programming system. MIPS, the full form of MIPS is the microprocessor without interlock processing system. What is that interlock is this one. This one, what I said is this interlocking. When there is a dependency of a next step over the previous step output, then we say that there is interlocking. If that sort of interlocking is there, when there is a little bit deviation or delay in the generation of the outputs, then the no-op instructions will be provided, and that MIPS will be handling that sort of what you say, the interlocking element that is needed for continuous iteration without any hitch. Okay, so what are the things like this MIPS processor have as a something like you can say the characteristics of MIPS, if you can take. See here. First characteristics, or what you say, first feature of the MIPS is it is having uniform instruction length. It is having uniform instruction length. What is the meaning of that is every instruction, any instruction of arithmetic or logic you take, it will have 32 bits. Whereas for CISC, if you take, it will be varying from 18 to 16 or 16 to 32. That means it depends on what is the type of instruction. Something like a jump instruction is there, or a arithmetic addition instruction is there, or comparison instruction. That like depending upon the type of instruction, the CISC instruction will be varying in the code length. Whereas for the RISC, it is whatever may be the instruction, that size or the number of bits in the code will be. Hello? Unmute, mute yourself, no? Someone is speaking. This will be 32 bits and it is something like we can say that Um, what is byte for an information?
8 bits.
Byte is 8 bits. Okay. 8 bits to 16 bits. Your CISC will be of byte to nibble length sort of thing. But this MIPS is 32 bits. So that uniformity is there. That means there won't be any confusion now. Bits are constant, but how we try to split that bits into is dependent upon what is the type of operation we are performing. Okay. And here the formats of instructions are very few. This is one more advantage you have. Few in the sense, something like which is for encoding purpose. We need to use different fields of instruction, and this will be uniformly implemented, and it will be for decoding and encoding both the things, because the formats are very less in number. The decoding and encoding will be very simple in your RISC processor. That is one advantage we are having. And addressing modes also, the number of addressing modes are also very few. Are I think I can say this is very little in the sense, something like one or two memory addressing modes only it will be having, one or two addressing memory modes. So there won't be any confusion. So you need to have a vast knowledge if you want to implement with the CISC. But only two addressing modes if you have, it is easy to understand and easy to write also. Okay. And it will be handling with large number of registers. Something like this, we can say it is a register to register transferring iteration. It will be a register to register transferring architecture sort of thing. That means hardware point also, it is not taking huge varied components, rather it is depending purely upon the registry uh, interactions, or what you say, registry iterations. And something like here, another element is that we have only load or shift architecture. What is the use of this load or shifting is something like, um, loading or shifting is between the memory and the register. Say an instruction is given as a load, say it will transfer the memory data to register, and shifting operation it will transfer the registry to memory. Something like how, like I can give an example, something like that. So if you are giving an add instruction, where from that add data will be coming, that registry data will be coming in, a memory location will be specified. From that memory location the data will be collected, that will be put on to the register, and here the registers, in the register the addition process will be completed, then it will be kept back into a specified memory location. So this is as simple as a transfer of data between a memory and register. Okay. And something like, there won't be any side effects. There won't be side effects. What are the side effects for us is something like when we perform iteration, overflow, underflow, something like what you can say, condition codes. Condition codes means something like flag conditions. In microprocess, because you are not used for microprocessors, I am telling this. Flag means something like a condition is um, like after performing any iteration, a condition rises. Say a carry is coming over, or a, what you say, sign bit is changing. Okay, all these will be highlighted as a flag, an indication in your program. So these conditions are the after effects of the iteration. Okay, when you perform an iteration, there can be a carry generation, a sign bit changing, or into the sign bit you will have the value of the result overflow. All these are something like we call them as side effects. Okay, so there won't be any implied side effects coming in, because your this risk element or your risk architecture is having huge number of bits of locations, so it will be able to accommodate a huge data. So there won't be any type of side effects coming. These are the major, what you say, um, advantages of the risk process compared to CISC. Okay, now what is this when you are computing? Normally, previous architectures like the manufacturers, something like Intel or your IBM fellow, they have earlier named this as SISC. And if you pronounce this, what is this? A simple instruction set computing. Actually, when you pronounce, these two will be pronouncing similar. So earlier it was given this format, but there is a confusion between CISC and CISC. The way you pronounce, there is a confusion, so they renamed this as risk. So maybe earlier version of textbooks, if you will be seeing, risk will be given as SISC, CISC, not CISC, CISC. So don't get confused with that. You better go with risk only. Okay. Um, so this architectures of CISC and risk, if you compare, so CISC, we cannot say that it is completely disadvantageous. They has the advantage, but um, the instruction encoding is denser in CISC than the risk. Okay, the fixed instruction width of risk will be leading us to more bits than necessary. Okay, some of the instructions, something like here it will be fixed as 100 instructions. Here it can be varied as 800 to 100 instructions, sort of. There is a variation you can have, but here we have fixed number of instructions for addressing all types of iterations that will be performed on the processors. So risk will be more advantageous compared to CISC. CISC is also an useful architecture, but comparatively for a beginner, risk will be a preferable sort of architecture, or what you can say, process. So when you take this risk fellow, we can say that this is single instruction computer. You can name this as single instruction computer. Why this single instruction name is coming is, in the 132-bit set of instructions, we are able to mention all types of iterations. Okay, or all types of what you say, instructions you can incorporate in one instruction itself. We don't need multiple instructions. So what are all the instructions that your Mips can be giving? Mips ISA is, you can have arithmetic instruction, logic instruction, and next one you can have another memory access instruction, memory access. I think I can move this. So these are our tables of instructions, what I can show you. See. Another type of instruction is control transfers instruction and sorry, unconditional controls transfer. So these are the different Mips ISA instructions what we have. First one is arithmetic instruction. As I said, this is 32-bit. This is 32-bit instruction. Each instruction like it is said as one single instruction. No, here this will be registers. Each instruction will have registers of three. In this three, two will be the source registers and one will be the destination register. What is this source is onto which what the iteration has to be performed, the values will be stored in source register. After your performance of the instruction, what is the result you are getting will be going to the destination register. Okay. Now see, this is your arithmetic instructions, set of arithmetic instructions what you have. This is the table what I'm showing here now. See if you can understand, I'll let you know. See, this is all 32-bit length. Every instruction is 32-bit length. See, it is given like M1. There's the meaning. So if you can see, this assembly code is $S1, $S2, $S3 indicates that the content in S2 will be added with S3 and here it will be stored in S1. Now here you have add add u. If you are having add u means u is unsigned. What is the difference between these two is, if there is any overflow, the unsigned numbers cannot identify it. Whereas as if you take the signed one, the overflow will be detected. U means unsigned. Unsigned, if you are taking, the overflow detection will not be done. What is that overflow? What is that overflow? Like magnitude increasing more than the number of bits. Say 4-bit value if you are adding and the magnitude is exceeding that 4 bits and going to 5th bit, it cannot be taken as carry or what is a sign bit. Na? So the overflow cannot be detected if it is unsigned. So that is like if you don't want to have like a small numbers, if you have, you can go for unsigned addition. So this is an immediate addition. Add immediate. Add I indicates that what is the value that is to be added, a constant value will be already indicated. Something like I mentioned something like this. Add I dollar, say M1, dollar M2. These are the names of registers, just a name I'm giving. Say I take 100. Okay, this is constant. I'm saying immediately add the content of M2 register onto this value of 100, then you store that into M1. That is the instruction. Okay, so here again add immediate unsigned is, this is not in a position, this instruction if you are using, it won't be able to identify any overflow happening in the process of adding the content of a constant with the data of your memory location. Okay, and the same thing, multiply and multiply unsigned if you are taking. Now this multiplication, you have one thing. When you are adding, okay, you are adding say n bits are added to n bits. Now this can be having 1 bit of extra element happening along with n bits if there is an exceeding that what is a range of value. Okay. That means we know that something like n plus 1 is indicating an overflow. But if you multiply n bit with n bit, naturally we need to have 2n storage thing. Like we are using this with a memory. Now, here for multiplication operation, we will be using the double the location of n. Okay, that means we try to say that the half portion will be occupied in the lower thing, and the next higher portion will be occupied with the next set of half result. Okay, say 16 to 6 30, like you are getting 12 bits of result. Say first 6 bits comes here, next 6 bits will be coming here. That means high and low values, like the locations will be assigned, and there the data will be stored. See here, something here we are giving. Now multiply S2 with S3, means content of S3 will be multiplied with S2, and we are indicating that the content or the lower product value will be going to S3, and the higher product will be going to S2, sort of thing. That means we mention, say, the number of bits, which like lower bits or higher bits has to be occupied at which position will be mentioned clearly. In the division also, we'll be using like 2n memory location, and we try to take the higher or lower, the quotient fellow, and the other thing will be remainder. Like you can interchange this. Okay, now this is move instruction, just moving the values. Like here, after performing your multiplication and division, we try to use this set of instructions to indicate which set will be going to which memory location. Okay, if you say that move high, means your high end of the product value will be going to the high location, or that means that portion. Say if you are having this two sets, n bit and n bit of data, this is lower portion and this is higher portion. So now you indicate which portion has to be stored in which location. That will be instructed by these two instructions. This will be used for specifying the locations. Now these are the set of what you say arithmetic operations. Only these we have. Any other iterations will be taken as the logical operations. Okay, all your add, subtract, your multiply, divide, everything comes into this instruction set. Now the other one is logical instruction. What is this logical instruction mentioning? Again, this is a 3 address format only, and here we are taking S2 and S3 as the source registers, and S1 is the destination. Okay, these are your what you say, the logical operators that will be used in your Mips. And immediate, that and is the contents of the registers will be taken, and the logical operation will be performed, and that will be stored onto your S1. And OR operation, the same thing. The contents of these two will be ORed and stored onto S1. Now immediate is the content of S2 will be and with the k value. K is a constant value. Okay, and this will be extended with like 0, it is said. Okay, k is extended with 0 first, and then it will be added to the content of your S2 location, then it will be stored onto S1. Okay, say if you are having complete set of instruction, we said 32 bit now. If this k value is not 32, you can pad that with 0. That is the meaning here. If the k value is not 32 bit, you can pad that with 0. And this one, shift left or shift right logical operation. How many bits you have to shift will be indicated by the constant value. Okay, say a value what you are indicating here, the content of this will be shifted with the constant 5-bit value of k. That is the standard what will be followed in your logical instructions. And the other instruction in your Mips is this. Something like if you have the load instruction and load and shift, I said, no? What is this load instruction mentioning? See here. Here, if you are taking the load, what is to be loaded is from the memory. As I said, no, load means, sorry, load if you are taking, it is from the memory to the registers, it will be storing the data. Shift means, shift iteration means from the registry, the data will be stored onto memory. That is the major difference you have in these two instructions. Okay, say the load word means here what is the element of S2, that means this is the memory location. Onto that you have to use the k bits offset, the constant k bit offset will be used, and this content will be added or it will be loaded or shifted onto the register S1. What is the meaning of this is, say something like this. If I say $100 S2, I'm saying. What is the meaning of this is, I should be, say, if this S2 is having, say, a value something like 1000, that will be added with 100, and this will be stored onto your, what you say, the register. This is your memory location. That will be added with the constant value, and that will be stored back into your memory location. Okay, so you can have the full word or half word also. Like if there is no mention of, like are you taking the complete information or half the information? Like this will be load word means complete information will be transferred with an offset. With an offset. Half word is that only the, what you say, the first bit or second half will be loaded. Okay, and this one, store is different from load. Here also you can see here, load operation and store operation if you perform. Loading is taken from the memory with the offset back into the register. This is going to the register. Now, here the store word is something like in the registry, what is the information you have, that will be going to the specified address location plus the offset of, this offset will be 16-bit offset. This is the standard format. This is from registry, it is going to the memory. Okay, and here something like you can play with this load or shift store operations, either taking a signed values or unsigned value. What is the advantage of having a unsigned thing is, unsigned in the sense whatever the value you are getting, you will be using that completely without having an overflow checking. Okay, and if it is signed, you'll be having that element of sign bit evaluation also done. Okay, now here this is something like a constant value you want to load or constant value you have to shift. We'll be using these two iterations. Immediate, this is unsigned. Okay, this is byte, this is word, this one is loading the half word and storing half word. This is load byte, and this is unsigned, and this is storing the byte. Okay, these are the different instructions which is your memory access instructions. These call that as memory access instruction. Okay, and next one is your control instruction. Something like here, branching of the ASMs we have seen, control instruction, something like jump address is there. Like we had this jump address on one condition. A condition is satisfied, then go for this jump address, or else it will be sequential sort of thing. I think why I'm taking this example is we have done this and we learned this, so it makes to be simple to understand. Same while um, condition is satisfied, a condition is satisfied, then it has to go to the branching address. Okay, and a condition if not satisfied, it has to go to the branching address. This is the two instructions we are having: branch equal, branch not equal. Okay, indicates that, say here, um, here this PC is nothing but your what is a program counter sort of thing. From that, like where exactly your like offset has to go, it will be informed in this what you say exact location. Okay, something like this we try to take 4 times, like 4 times means this is offset by 4 times. Okay, something like, say I take an instruction of branch equal eq on dollar, say s1, dollar s2 with say 25 data. Now if I'm performing, this is uh, a program counter plus 4. What is this plus 4 is, normal the opcode will be taking 6 bits of information, and the later of your 28 and so on bits will be used for the other instruction information. Okay, so we try to take the program counter offset for the next instruction. This plus 4 means that instruction uh, like a jump sort of thing, where your next instruction will be placed, plus of your 4 times of 25 means this is equal to 100. Okay, that means this goes to program counter, the present program counter offset of 4 plus the instruction specified. It jumps to this instruction when the content of S2 is equal to S1. That is the condition. When the content stored in this location is equal to this location, this will be offsetting to another address location which is placed at program counter offset of 4 with 100. Okay, this is the instruction meaning. Okay. So the effective element or effective address, next address, will be taken by the offset value. That is the meaning here. So it is now, this is if it is not equal, as simple as this. If this content is not equal to this, it will be going to PC plus 4 of the value what is indicated here, the 4 times. That. Okay. With the sign extension, you can take if it is signed or unsigned. Okay, this is conditional. If this is less than or greater than, comparison if you are doing. This is equal, this is comparison, and this is unsigned comparison. This is for unsigned comparison. Okay. The other one, complete, what are all the instructions we have taken. Now, if I can give, this is our jump address, jump instruction, we can say. Unconditional. The previous, these are conditional. This is unconditional jump transfers, we can say. Normal jump to the address with the offset bits of whatever the address you are mentioning here. There won't be any condition here. Okay, just whatever the value that is indicated, directly to that memory location, the jump will be happening. Okay, and completely all these instructions, your arithmetic, logic, or your jump or comparison, load or store instructions, everything, we can accommodate or we can classify that into three formats. What are those formats? Are the registry format, R format, the instruction format, or J format, R, I, and J format. Every format is 32-bit in size. I'll show the table. Table is there. Yes, this is the table. See here, every format you take, every other, whatever the instructions we have seen so far, all these instructions encoding, I can say this is Mips encoding, is classified into three formats. Okay. Now, R formats are your arithmetic operation formats, are R formats. All your ALU formats or ALU instructions will be following R format. Okay. What is this R format is, uh, which will be having three operands, or which will be in need of three operands, the R format will be used. Any format you take, the first 6 bits, that means your MSB bits, will be the opcode, the operation code mentioning all these operations. What are all the operations? Add, subtract, compare, equal, all these instructions what we have seen. Okay, so 6 bits will be for opcode. R format, see, these first, what you say, the three sets of registry fields are there for R format. Okay. And these three registers, if you can take, one will be the destination register, and two will be the source registers. Okay. These two will be source registers for us, these two. And this will be destination. Okay. And this is shift amount. How much amount, or what is the next field uh, of the jump or the like what you say, the opcode where you have to find, will be given as the shift field. Okay, that is how much amount of shifting is to be done in the shift instruction will be mentioned in this what you say, 6 to 10 bits, bit 6 to 10. Okay, and what is this F code is the function code, or the field which is mentioning the function. Function code will be given here. Okay, this is an additional opcode. This is like you can use or you can skip also. This field is whenever you want to use this function, specific function to be mentioned, then you can use this F code. Okay, so completely your R format will be having three registers, one shifting like instruction and one function instruction. So altogether this is 32-bit only. 0 to 31 bits it will be using. The MSB 6 bits will be opcode, then remaining we are dividing that between the registers and the instructions. Okay, this I format is a pure arithmetic or what you can say, load or store. Arithmetic or load or store instruction, the I format will be used. Okay, and the branching instructions also, the I format will be used. Okay, and this is the what you say, the source register, and the what you say, onto which the offset has to be performed, the opcode has to be performed, will be mentioned in R of T. Okay, and J format is your jump instructions. J format will be used for jump instructions, because this jump instruction, we don't need a register there. So directly the remaining bits, okay, the remaining bits of out of 32, uh, 6 bits taken out, the remaining bits will be used for the jump address, or what you say, the target address, or the next address to which your processor has to reach. That will be directly shown in the target address. which wherein the registers are not needed. Whatever like instruction where we are not taking any registry help, then directly we can use the J format. So complete set of instructions, if you can note like these previous tables, if you can take, you will be dividing them into these three formats only. These are the three formats what we are having. So just one second, show the other things. Yeah. So completely, if I take the formats, see here, add, add, subtract, or what you say, simple add, ALU, arithmetic logic operations are taking the R format. If you can see, these are the formats we have mentioned. Okay. And something like immediate operation, if it is there, we are going for I format. Immediate operations, we are going for I format. And J format, if you see, jump format, jump on something equal, jump all those things, we will be going for simple jump, or simple jump on some condition, we are going for J format. So how many bits of instruction is taken is clearly mentioned in this table. If you want, I'll share this things to you. If you want, you can record this PPT sort of thing. Okay, and see here. Completely, when I want to put this into, like if I want to implement the subset of MIPS, I need to mention the data paths and what is the way it is being getting executed, we have to take. So implementing this subset, the design of data path is to be done. What is this data path is, what are the steps that will be taken up to implement all these instructions? First is, the processor has to fetch the instruction, and after fetching the instruction, it has to decode the instruction, like what is the iteration that has to be performed. Instruction decoding, we say. Instruction decoding has to be performed to identify what is the type of iteration it has to be performed, that is mentioned in the instruction it has to decode. Next one is something like it will be reading the operands, and it will be executing the instruction, and it will be taking something like using the write read operation sort of thing, write read operations and execute the instruction. This is not something new for us. Any instruction is given, you have to first fetch the instruction, you have to understand what is the instruction mentioning, and like a human being, if we are taking, means we are something like this can be taken as a problem statement, understanding that, then trying to like decode what exactly is the hardware that will be performing this, and trying to put it into one design. So for our processor, it is something like getting the instruction, trying to understand the instruction, that means decode and implement the instruction. That is the only iterations that it will be performing. For that, the fetching unit, okay, this is a fetching unit. What is it, or how is it fetching the instruction? Okay, this program counter, you have a program counter that will be storing the huge set of instructions that like the processor will be handling, and these will be selecting one of the possible what you say, the instructions that are listed in our previous tables. What are those? Is p plus program counter plus 4. This is the instruction which is something like other than branching or jump instruction. The next instruction will be given at program counter plus 4. I think in the previous table we have seen the next instruction will be placed at the present program counter plus 4 position. The next iteration will be readily available there. Then next, the program counter branching is something like branch on not equal or branch on equal sort of instructions we have now. For that sort of instructions, it will be with an offset. Okay, with an offset, what are the instructions, branching instructions that will be taken? Like you will be selecting one of the instructions that are being listed in the instruction. That is the meaning here. Okay, this is your jump instruction, and this one is your what your normal without any condition, a jump instruction, if it is mentioning the register where the jump has to be happening. So for like after getting this, what are the iterations that will be performed? Like is through, like you are getting an instruction from one of the possible four sources, and this program counter will be able to store that information. Now this has to be given to what you say, the overall data path. The overall data path block diagram sort of I'll show. See here, this one. Here, I again, you are able to see that three addressing thing registers, where two source registers are there, one destination register is there, and this data will be selected, and this offset is something like based on signed or unsigned values. This offset will be used, and between this, like it will be selecting between like read or write operation. If it is read means where from it is will be reading from the memory location, na? Write is to the memory location. Reading means taking from the memory location. So the decision of the data what is readily available will be like read or write onto the memory location will be given by this mux. This mux will be taken without any offset, or with an offset we have to perform this ALU operation will be given by this mux. The choice of your next program counter thing will be given here by this mux, and this mux will be giving an iteration or what you say condition of reading or writing the data what is processed. So this is your what you say computation and memory instruction, we can say. This is data path computation and the memory instruction, like whether you are writing or reading the data from the memory or to the memory, it will be taken. So completely, if I take the fetching operation and the computation and the memory instruction operation completely put together, if I put together, it will be the implementation of subset. Now both the things I am putting in here, if you can see this. Okay, this is our fetching. This portion is fetching, instruction fetching, and this portion is data path. This one, this segment is your data path. Okay, now how many muxes are seen? What are their functions? Let us see. Now you have mux1, mux2, mux3 and mux4. Four muxes are there all together, and you are doing the operations of the fetching and your iteration, and again back the storage. Okay, like these are done along with what you call it as a normal instruction, a jump instruction, or immediate instruction. All this will be done, or conditional instruction. Okay, these type of instructions you are able to perform with this simple overall data path set. See here, the first mux here, this first mux is the selecting the destination register. Okay, selecting the destination register will be done by the first mux. Okay, second mux will be this one. The second mux will be the ALU, where from your data should be given to the ALU will be selected by the second mux. Okay, so this is something like in your R format, in your R format of instruction or in your I format of instruction, the immediate address or the offset address, the immediate address or the offset address has to be selected, and that will be given to your ALU for its next iteration or next address evaluation. Now, this third mux, this one, it will be selecting between the memory or the ALU output, between your memory or the ALU output to be written or read, to be written or read into the memory location. That means your destination register. Like whether you have to read or write will be performed. If you can see back this path, that indicates that whether you are performing the read or write operation. This will be instructed by the third mux. Now this fourth mux will be selecting the one of the four possible program counter values. Okay, like this is depending on what type of instruction you are taking in. All the four instructions we have seen, these four instructions we have seen. This is normal your arithmetic operation, this is your jump operation, this is your conditional operation, this is unconditional operation. So one of that instruction, based on your instruction what you are giving in, based on this instruction, it will be choosing the next address location of the program counter that will be given to here, that will be going to your ALU operation, and that will be giving an output which is either written or read onto the memory location. Altogether, say you have the registers, each register is of again 32-bit size, we are saying. The huge data that can be stored in your Mips is able to handle all types of instructions and all types of data, or what you say sizes of data sets. So this is one what you say basic level of understanding for the Mips and the subset of Mips. So if you, until this, if you can understand, that itself is a big issue for you at this level, because you are at the beginning level only, and if you had read your microprocessors, this will be very simple to understand. But you didn't read the microprocessor a little bit, you need to do the decoding sort of thing of every um, table whatever we have given. So completely if I put that into one set of what you say a table thing, how many number of, or how many number of bits each instruction will be taken, you can take up into this format. Okay, this will be helping you to understand this better. Okay, what is the simplest thing, or what is the simplest iteration is jump, only one, simple decoding. What is the lengthiest thing is load iteration. You need to read the address, you have to do the offsetting, access the memory to bring the data and perform the said instruction, then you have to load the data onto the register. This is the lengthiest path, and this is the shortest path you are having. Jump instruction takes the shortest path, and the load instruction takes the lengthiest path. And your ALU branch on equal, or um, the store or load registry sort of thing will be equal, three step if you see. Okay, this is your overall what you say Mips thing. I'll share this PPTs to you, or this segments. You can understand them, you try to read it on yourself, and if there is any doubt, you try to interact with me again back. Okay, so maybe I'll stop here. This completes your Mips instructions. Any doubts you have, you can ask now. Section A, I think Vedic multiplier we have seen in DSD 1, I think.
Yes, ma'am. Last time we had seen it, ma'am.
Uh, so section B, they need to get it. You remember that Vedic multiplier, section A people? Only that topic is to be dealt for them.
Yes, ma'am, we remember.
Okay. But still, 1 second, I'll do that and try to wind up this session. See, say a 3-bit Vedic multiplier, if you have to set, say A0, A1, A2, B0, B1, B2. Okay. So section A people, can you give? What is the first step? This is something like a crisscross sort of multiplication and addition sort of thing. Something like first we have to take the product of A naught, B naught, then A1, B naught plus A naught, B1. That means this one. Next step is this one. Okay. Then the other next step is this one. That means A naught B2 plus B naught A2 plus A1 B1. Next is A2 B1 plus A1 B2. Next is A2 B2. This will be giving you the complete what you say, the result of your iteration. Say 2-bit, if I give, you can understand that very well. B0, B1 if it is there. First will be A0, B0. Second will be the crisscross, and third. 3-bit means you'll be having 5 steps. 2-bit you'll be having 3 steps. The minimum of minimum multiplication I took. So something like this, say I need to multiply 1, 2, 4. How I can do? This is 2 4 8. Next, 4 plus 4. This is 8. Next, this one, 2. What is the result? You will understand that logic. What is that we are performing? Your hardware, I think A section people, they remember the hardware. No answer.
Man, don't remember the hardware.
Okay, okay. So this is 8 and this is your 2. This is correct or not?
Yes, ma'am. It's correct only.
This is 1, this is 1, this is 1. Same way, if I want to get, say, 121 into 212. As simple as this. Let me give a try this one. See here. 1 into 2, 2. This is 4 in plus 1. 4 plus 1. Next. This one. This is 4 plus 1. Next it is 2 plus 2 plus 2, 6. Next, 4 plus 1, 5. Next, 2. Should be coming. Is this correct? Is this correct?
Yes, ma'am. Yes, ma'am.
So for this, what is the hardware needed? What is the hardware needed? It is simple AND gate logic, and what you say, full adder will be there, and an 2-bit adder will be there. 2-bit adder is different and full adder is different for us. Say a 2-bit adder is only the incoming bits will be added, and it's, we won't say that carry will be added. Addition is complete addition, 2-bit complete addition, and this is full addition. Normal full addition is a plus b plus ci minus 1, and this will be AND operation. So complete, these are the components we will be using for this Vedic multiplier. So next are I'll be teaching that in your theory class itself directly. A section also I'll give that hardware for your Vedic multiplier. You are saying you didn't remember that, na? So any doubts you have regarding this Mips sort of thing, I can give you some clarity, or else we can stop the session.
No, ma'am. It is clear.
Okay then, okay.
Ma'am, even if it's regarding the doubts, we'll have class on Monday, ma'am. Like for E-section.
Yeah, Monday we'll have. Monday, anyhow, like
Yes.
after your spring spree, if classwork will be cancelled, we don't have
Uh,
class, no? That is
like,
okay.
ma'am, will you be taking class tomorrow, ma'am?
Tomorrow for,
Yes, ma'am.
no, completed.
So on Monday, ma'am?
Monday, I'll take Monday.
Okay, ma'am. Okay.
Yeah. So I'll stop sharing now. See, for this Mips subset, you can refer to your Roth book. Charles H. Roth, it will be clear. You have the textbook? Yeah, the Charles Roth will be clear, and all these tables are taken from that book itself. So you can refer that back there. Okay. So I'll stop the session.